Use the normal approximation to calculate the probability that x is greater than or equal to 19 for n equals 32, and the probability is 0.5. Okay, so normal approximation means we're going to use the bell curve to approximate a binomial probability. So first thing we need to do, as we saw in the other videos, is draw the bell curve, right? And on the bell curve, we need to label its mean and its standard deviation. So let's draw the bell curve. Over here, we'll have the mean and standard deviation labeled. In order to calculate the mean, we have to do n times p. That's the formula in binomial probability to get the mean. So n is 32. The probability is 0.5, so that's half of 32. We'll get the answer 16 for the mean. For the standard deviation, the formula is the square root of n times p times q. And of course, in that case, it's going to be the square root of 32 times 0.5 times 0.5. Please remember that the p and q must add up to 100%. So if p is 0.5, the q has to be the other 50% to add up to 100%. Okay, so let's figure out what that is. What's the square root, of course, we know will be, if 32 times 1/2 is 16, then half of that, of course, is 8. That's going to be 2 square roots of 2. Let's see what 2 square roots of 2 is as an approximate decimal here. So the square root of 8. We do that, we get 2.83, right? 2.8, let's say 28, just to give it a few extra decimal places, get it out to 3 places. So 2.828. 2.828 is our standard deviation. Now from there, label your z-axis and your x-axis, putting the means on the curve as well. So the z-axis mean is 0. The x-axis mean here will be 16. Remember what the x-axis represents. X is the number of successes out of 32 trials here. So x is greater than or equal to 19 is the problem they ask us for. So let's put 19 on the right-hand side of 16. Let's draw a line here. And then we'll shade the tail to the right. Right, so we're looking for the area in the tail here, but we have to remember this is a binomial approximation problem, so we're going to be approximating the binomial probability by the normal bell curve. And when we do that, we have to do something called continuity correction. So we actually have to start a little before the shaded area. Whenever we're sweeping to the right to accumulate probability, we have to start just a little bit before. So we should be looking for the number that's right here just before. And the way we're going to do that is we're going to subtract 0.5 from 19. So we're actually going to use 18.5 as the value that we're going to convert into a z-score. Okay, so let's do that then. Let's convert 18.5 into a z-score. So we'll have x minus the mean over sigma to calculate our z-score. That's going to be 18.5 minus the mean, which is 16, divided by 2.828. When we do that, we'll have our z-score that we need to look up on our table. So 18.5 minus 16, of course, is going to give you 2.5. And you divide 2.5 then by 2.828. When you do that, you get the answer 0.88 if you round off to 2 decimal places, which we are required to do if we're going to use our z chart. So 0.88. All right, let's go look up 0.88 on the z chart and see what area we get. Please remember that that area will be from here to here, correct? That's not the area we're looking for, so we'll do 0.5 minus that area to get our final answer for the tail. Okay, we're looking up 0.88 on the z-table. There's 0.8, and 8 is all the way across to the next to the last value, which is 0.3106. 0.3106. Okay, so we found our answer to be 0.3106, 0.3106 here in the white space, and then the area in the tail, of course, is 0.5000 minus 0.3106. Okay, so let's do a little borrowing here. 10 take away 6 is 4, 9 take away 0 is 9, 9 take away 1 is 8, and 4 take away 3 is 1. So we get the answer 18.94%. So if I write this statement out, it's the probability that x is greater than or equal to 19 is approximately equal to 18.94%. All right, very good. So that's the answer using the normal approximation. Now, one thing I want to talk about here before we end this video is how accurate is this approximation technique? So we're using the bell curve to approximate something that's binomial in distribution. How accurate is the approximation? Well, let's actually see what the real answer is for this problem if you use the binomial formula. Now, on my calculator, I've written a program that does this. The calculator has its own program, but I actually wrote my own program instead because I think it works a little better than theirs. So I selected binomial probability from my program menu. I hit enter. It's asking me for n. Our n is 32 in this problem. Our probability is 0.5. Then our x value here is 19, or related to 19 at least, and I want 19 or more, so I'm going to push option 1 here, x or more it says, so that's 19 or more. And when I do that, I get the answer 0.1885. 0.1885. So you see we're a little different, right? The original answer that we got was 0.1894. If we subtract off 0.1885, you see our answer is off by just 0.0009. So that's the difference. It's 9/10,000ths away. That's basically the answer difference. So it's very close, right? In fact, one of the reasons why it's so close is because this p is equal to 0.5. Another reason why it's pretty close is because we used continuity correction. Because we didn't use 19, we used 18.5. That little bit of correction that we used actually makes a big difference. Let me demonstrate that instead and see what would have happened if we had used 19 instead. The z-score when using 19 would have been 19 minus 16, right? And then we would have divided that by 2.828. So we would have got the answer 1.06 for our z-score. Now what happens if we use that on our table? Well, I have a program in my calculator that the calculator produced, of course, that says that the area from 0 to that new z-score of 1.06 would have been basically 0.3554. And if we had done 0.5 minus that 0.3554, so we're just doing the problem the way we would normally do it on paper, I'm just doing it in my calculator, we get the answer 14.46%. So instead of getting 18.9, which is very close to the actual answer, we would have gotten in our calculators, or we would have gotten on our work if we had used the 19 instead of the 18.5, we would have got 14.5%. So quite a big difference in the answers, right? It would have been a much different answer, not nearly as close as it was by using the continuity correction. So again, two reasons why this is very accurate. For one, it's the most accurate, the approximation technique, when the p is 0.5 or near 0.5. So that's helpful. And the other thing that's really helpful is this continuity correction. So it's very important that you don't forget to do it, because if you do, you'll have a lot more error in your answer. But either way, as an approximation technique, it does a very good job. For this particular problem, we saw that it was only off by 0.0009, right? It's only 9/10,000ths off, right? Or in other words, 0.09% off. So it was a very good answer from our approximation technique. And considering that in many cases, it's a much faster way to do the problem than actually using the binomial formula, it's a great tool to have available to us.